We finished our section on the Fourier analysis of periodic and non-periodic signals, as well as systems and their response to periodic and non-periodic signals, and taking a look at things in the frequency domain. So now we're going to be changing gears and taking a look at sampling of signals and then reconstruction of signals from those samples. And we're going to be using a Fourier domain perspective because that informs some of the practical decisions we have to make when it comes to sampling and reconstruction. So first off, just as an introduction, what exactly is sampling? So sampling is the act of periodically measuring and storing the amplitude of a continuous time signal. So we're starting with a continuous time signal, and then what we are doing is just measuring the amplitude at certain instances in time. The idea being that we want to eventually construct a discrete time signal with those measurements. And we just indicate this with a switch that periodically closes at times n times capital Ts, which is the sampling period. So we're starting from a continuous signal. We're going to sample at regular intervals, Ts, so that's the spacing between samples. And we end up with a discrete time signal at the end of the day. The way that we would think about this mathematically is we're starting with our original signal and only taking the values where t is equal to n times ts. And then we're using those values to populate the array that holds the discrete values in it. For instance, we might have a continuous measurement of the temperature in the room at all times t. And let's say we take samples every 10 minutes. Then in our discrete time signal, we are storing the temperature, but just at 10-minute intervals. Okay, so we now have this picture of the continuous signal and its discrete version. What's interesting is that under certain conditions, that original continuous time signal can actually be that means perfectly reconstructed from the samples. So that would be actually going from the samples and reconstructing the signal it came from. But in general, we can only get imperfect or approximate reconstructions. But how do we choose this sampling interval, or alternatively the sampling frequency? To get a good enough approximation, and this is where the engineering comes in. What is good enough? Are we confident that there's no significant signal variations in between samples or consecutive measurements? If not, if it's actually a slowly varying signal, for instance, could we have waited longer? That has an implication on the amount of data we have to store and the amount of bandwidth we need to send that information. As I said, under certain conditions, we can completely reconstruct the signal. And the idea is that we are reconstructing our signal from the samples using some basis functions. And we're going to talk about that quite a bit later. But in this picture, there's actually an example of the original signal in the blue line. The red dots are the samples. And you'll note that a perfectly reasonable signal that passes through those red dots is this green line. And clearly this is not the same signal as the original one. So what's going on here? So I still will say that we can perfectly reconstruct it, but how do we actually do that? It seems sort of weird because when we sample, it seems like we're losing information. We're losing what's going on in between samples. But so how is it possible to perfectly construct that signal? Another way of thinking of it is, does the signal behavior between sampling instants constitute worthwhile information, or is it redundant information that we can predict anyway? If it's redundant, then we can actually perfectly reconstruct that original signal. But how? So as an example of sampling, we know that audio signals, for instance, on a compact disc, so the data is actually stored in a format called the WAV format, which is that we take the amplitudes and convert those to binary numbers, which represent those amplitudes. But the sampling frequency is 44,100 samples per second. And if you remember, our audio frequencies are in the range of 20 to 20,000 hertz. So that's a little over twice the highest frequency of audio. And a 5-minute song is about 50 megabytes in size if you're using 16-bit encoding for the amplitude. Now the question is, how does an MP3 get that same song down to about 6 megabits? Or megabytes, sorry. Well, that's for later on in your career as an electrical engineer. In third year and fourth year, you can actually learn a little bit more about that. Another example of where we use sampling is for images. So a digital camera actually is a two-dimensional signal. An image captured by a digital camera is a two-dimensional signal. Each pixel or little box in the image contains digital information about the color in that box. So both what is the color, but also what is the brightness of that color. And then a video file is really just a series of image files or snapshots that are taken at consecutive time intervals. And if you just stack those, and think of it like a matrix, as long as you're sampling at a high enough in time, then when you stitch together those images, your eye can't tell the difference. It just thinks it's a continuous video that's happening. But why do we sample? Why not just stick in the analog domain all the time? Well, it's actually much easier to store digital information than it is to store analog information or signals. Furthermore, we want to be able to manipulate and modify our signals, and it's actually easier to do that in digital format than it is in analog. And that would be for signal processing or image processing and all sorts of things. Basically, it's just filtering. It also allows us to take advantage of computers for faster computation. And digital signals are actually much more robust to the effects of noise and interference, and we can actually do error control and coding with digital signals, which we can't really do with analog signals. Clearly, it is everywhere in your life, and so it's good as an electrical engineer to know what's going on when we're talking about digitized signals.